Okay, so straight line graphs, and we're looking at modeling with straight lines. So we're looking at situations in the real world where y is proportional to x. So hit pause, make some notes. When you're ready, hit play again. We'll look at a couple of examples. So in this example, we've got a graph showing an extension E of a spring, when we attach different masses to it. And we can see they're directly proportional because we've got a straight line graph. So as you attach more mass to the spring, it extends further and further. So they want us to calculate the gradient of the line first, then an equation linking E with M, and then finally you've got to explain what K represents. So in the first instance we need to find the gradient. Now the gradient is the rise over the run. If we take 2 points where the line crosses the grid nicely, like here and here, then we can find our rise and our run. So our rise here, if you look from here, 10 to 15 is 5. So our rise is equal to 5. And our run from 200 to 300 is equal to 100. So if I do the gradient here, part A, give me room. Gradient is rise over run, which is equal to 5 divided by 100, which is equal to 1 out of 20 when we simplify. So that's our gradient, otherwise known as K. In fact, I should write K here, because that's what they give us in the question. So K is 1 over 20. Then part B, they want us to write an equation linking E, which would otherwise be Y, because this is our y-axis normally, and M, which would otherwise be x. Now the equation of a straight line is given by y equals mx plus c. C is the y-intercept. In this case, it intercepts the y-axis at 0, so it's equal to 0. Y is the extension, which is E. X is the mass, which is small m. And M is our gradient, which we've calculated to be 1 over 20. So we can write the equation for this as E is equal to 1 over 20 of M plus 0, which we don't need to write. So that's our part B. Done. And then we move on to part C then. I'm going to change color because it's getting a bit crowded there. So for part C, what does K mean in this context? K is our gradient. So if we look at K, what it means is that if we extend the spring, each time we extend the spring by 1 unit, if we extend the mass by 1 unit, the spring extends by 1/20th of that. So we can write for every 1 gram of mass, the spring extends by 1/20th of a centimeter. Our units are centimeters there, and our units are grams here. So that's question or example 1. So make some notes. I would sketch the graph. Hit pause. When you're ready to look at another example, hit play again. Okay. Second example, we've got a container that's filled with water. A hole is then made at the bottom of the container. Depth of the water is recorded at various times and intervals, and we can see that in the chart here. So at 0, 10, 30 and so on up to 120, they're recording the depth of water as it leaks out. And we've got to determine, is a linear model appropriate by drawing a graph, deduce an equation, and interpret the meaning of the coefficients of A and B. And use the model to estimate when the container will be empty. Now this is an example where, because we are sketching it, we can use a lot of data from the chart as opposed to from the graph. Initially for part A we've got to draw the graph, so let's do that. So we've got time against the depth of water in the container, and if we plot it at time 0 we've got 19.1, 10 seconds we've got 17.8, 30 is 15.2, and so on. Now can we use a linear model for this graph? Yes, we can, because if you draw a line through it, it approximates to a straight line pretty much. Most of the coordinates lie on the line. I think that one's slightly off, but we can use a linear model for this. This is close enough. So that's part A done by sketching the graph, which I know you will do in your books. You can say yes, that works well. So hit pause, sketch a graph. When you're ready, hit play again. Okay, so we're looking at part B. Deduce an equation in the form D is equal to AT plus B, which is a straight line graph. Now we know our straight line looks like this. Y is equal to mx plus c. In this case, y is d. D is equivalent of y. And time, t, is equivalent of x. C is the y-intercept, so it crosses here when time is equal to 0. We can read that straight off the graph. When time is straight off the chart. When time is equal to 0, depth is 19.1. So our y-intercept is 19.1. I need to find m then. The gradient. Now I can't find any convenient points on here, so I can use the chart instead. I can take any 2 points on the chart. I'm going to take between 0 and 10 seconds, and I'm going to say m is equal to the change in, sorry, it's going to be the change in y, which is 17.8 minus 19.1 divided by the change in x, 10 minus 0, which gives me, it's going to be equal to minus 1.3 divided by 10. So it's going to be minus 0.13 is my gradient. So I can write my equation then as D is equal to minus 0.13 of t, which is time, plus 19.1. So that's my part B done. That's 19.1. Good. And it wants me to interpret the meaning of the coefficients then for part C. So before we do part C, you want to hit pause, copy these notes down. When you're ready, we'll hit play again. Okay, so what do the coefficients A and B mean? A is negative 0.13. So that means there's water leaking out of this container at a rate of 0.13. So that means there's 0.13, the depth decreases by 0.13 every second. So you can write that as, so we can say, oops, that the depth, so part C, decreases by 0.13 centimeters every second. And finally, what does B mean? I'm going to use a different color pen so we can see the difference. B is the y-intercept 19.1, which is the amount of water that was in the container at the start. or at time equals 0, time t equals 0, depth is equal to 19.1 centimeters. So before the hole was punctured in the container. And that's what it means then. So A is the rate of decrease, rate of flow of water out of a container, and B is the y-intercept, or the depth at the start before it leaked out. Okay, so hit pause, make some notes on that, and we'll see if we can find how much, what time the container will be empty. And for part D, when will the container be empty? Well, when the container is empty, our line will be crossing the x-axis, and the depth will be 0. So it's empty at d equals 0. So if we set our equation equal to 0, we have here 0 is equal to minus 0.13t plus 19.1. That's a t. If we rearrange it, bring this 0.13t over to the left hand side, I got 0.13t equals 19.1, and so t is going to be equal to 19.1 divided by 0.13, which is equal to how many seconds? Just going to check my calculator, and that will be 146.92 seconds. And that's when it's going to cross the x-axis. Good. So hit pause in a second to make some notes. This is different from the first example in that we managed to get the gradient and the intercept using the chart without resorting to finding the rise and over run on the graph. So you've got to think, when you get a question, you've got to think which method is best for me to use to solve that. So hit pause, make some notes. When you're ready, hit play again. Okay, for this example, we got in 1991, 18,500 people in Bradley Stoke. Planners projected the number of people in Bradley Stoke would increase by 350 each year. So write down a linear model for the population P of Bradley Stoke after T years. T years after 1991, and then explain why this model might not be realistic. So in 1991 there were 18,500 people, and we're going to try and use a linear model. If we're going to use a linear model, and we're starting in 1991, it would sort of look like this. If we sketch a little graph, it's increasing every year by 350. So our rate per year, 1 year, 350. This is our time, and this is our population growth P. So it's going to look something like that. And it starts in 1991 with 18,500 people. Okay, so in terms of a linear model, we write y equals mx plus c. Our intercept when we start is 18,500. X is our time. Our gradient is 350. And y is the population. So we can say that P is going to be equal to 350 x plus 18,500. So that's what the linear model would look like for part A. T years, oops, that's not an X, is it? That's going to be a T now. Time. Now change that. Let me just see if I can get rid of that and change it to a T. This is very temperamental when you're changing colors. That's much better. Part B, why is this model not realistic? Any ideas why the population wouldn't go steadily by 350 each year? Well, the reason is that the more people you have, then the more the population would grow each year. So it's more of an exponential growth than it would be exactly 350. So and you can write exactly that. Population would not grow linearly. So the more people, the faster population growth. Good. Hit pause, make some notes, and we'll look at some questions for you. I can tell you're eager to get some questions done. And exercise 5H, there are only 9 questions. Question 1, I don't know, they won't take very long at all. You could do the left hand side, so do A and A in question 2, and then onward then. Question 3, do all of it, and so on. And that's your question 9. Good luck. Exercise 5H, page 106.